I suppose you could say the precursor to Drives 2. So Drives 2 follow on from Drives 1. But how this the program is now set up, Drives 2 is no longer um, a compulsory module that persons had to take. So I may only see some of you and seeing is probably I'll have to say in quotes, but I'll probably see only some of you in Drives 1. But Drives 1 will introduce you first to three-phase systems. So that's where we'll actually start today, three-phase systems, and then we'll get into something that you would be familiar with already, the electromagnetism and magnetic circuits. So that will be Unit 2. Unit 3, we get into mutual inductance, which plays a part in all of the electrical machines that we'll be looking at. So we'll be looking at transformers. So that will be primarily the first machine that we'll look in detail into. And then, so single phase transformers. And then after that, we will look at DC machines. So, so the unit 1 is three-phase systems. Unit 2, electromagnetism and magnetic circuits. Unit 3, mutual inductance. Unit 4, single-phase transformers. And Unit 5, DC machines. There's also a Unit 6 on the syllabus, but it's usually very simple. It's about batteries. So usually that is something that I would just give you something to read upon. And work examples are usually a part of this course, so there will be a lot of examples, not only for that, but for almost everything that we're doing. So you will have a great opportunity to practice, and practice is one of the ways that you will actually develop the competence to succeed, not only in this course but in almost everything that you're doing. All right, so in a very short while we will start with three-phase systems. Um, but before I get into that, let me just mention about how we'll assess the course. Usually there is mid-semester tests. In previous years, it could be two and sometimes even three tests to kind of prepare persons. Not sure how it will be now. I understand that well, right now there are 32 of you here, and I understand it might get up to around 50 or so. So that will have a bearing on how we do the assessments, but we'll get to that in time. So there's the mid-semester test. The labs. We normally have about 6 labs, and with COVID and with the amount of you, I'm not sure how we will manage. But we won't be doing 6 face-to-face labs. We probably will be doing maybe 1 or 2. So in the lab, the others now I will ask the technicians to do a recording of the labs. This was successfully done last semester. Do a recording of the labs. They will take the results and then we'll send the results and the recording to you, the students, and then you will do your write up. Usually the write up for the labs, because the group size, the class size is usually big, is done in groups. So you can start thinking about who you want to be your group member. Usually about 4 persons per group. Usually don't want much more than that. And I really don't like the lone wolf kind of thing where somebody say, "Boy, I'm not going to work with anybody," and send me their labs to. I don't like that kind of thing. The group thing is supposed to help in certain aspects of your development also. So group labs submission will be, I think, part of the whole scheme. Right now, again, because of the class size and because of the experiences last the last 2 semesters, I'm not sure if I want to do online exams yet, and I think it probably will be much easier for me to do to have them schedule it, have the exam center schedule the exams and things like that. But later on as we go along, we'll iron out all of these issues. All right. Any questions before we start?
Um, Good evening, sir.
Yes. Good evening.
Just a small question, sir. It's about the recordings of the class. Um, Sir, how will we access the recordings?
All right. Well, that's an easy one. I can put it in Moodle when that is up, or I can send it to you by email. In previous times, I used to just send them by email.
Mr. Daly.
Yes, sir.
Um, all right. Well, what exactly is the reason why you want to administer face-to-face exams?
It's just too many people, and it's hard to manage so many people online. And
Sir,
the university offers it, so I didn't use it last semester, but I know a lot of persons use it. I think mechanical department, all of their exams were done face to face.
Sir Daly,
Yes,
uh,
sir.
one thing about the face-to-face thing is that some students that probably might be in this class now is based on the whole outline that the class would be online. They didn't bother to. They're international, so maybe they are in their own country and not here in Jamaica. So how would that work?
Oh well, for those who have special cases like those, we'll have to work out something.
Sir,
Yeah.
when will be the timing of these 2 labs that we'll be doing in person?
Are you asking a whole heap of information? With that, well, you're asking for some detail that I don't have yet, but you will be communicated in in good time so that you can plan.
Okay.
All right. So yeah, nothing will take anybody by surprise. You will get adequate notice about everything that we do. All right. So remember now that it is right now just a thought about doing the exams. Maybe in one of the shared facilities or in the auditorium, so you would have enough space for the persons who are local. So, but it's really just a thought now. I really have to see how the numbers look and all of that. I understand that it may reach up to 50. So that is one of the consideration. That is why that consideration is there. All right, but as I said, let's not worry too much about that yet. As we go along, we will kind of work out those kind of details. All right. All right. So what we're gonna do now is to start, and I'm gonna.
Excuse me, sir. Some persons are in the waiting room.
Oh, there are more. Oh, wow. All right. So we will be looking at three-phase systems for the next few weeks, and maybe I shouldn't have shown you the screen yet, but maybe you can help me understand what you know about three-phase systems. All right. So let me stop share for a while. Yes. Can you tell me what you know about three-phase systems? So remember, this is going to be a kind of interactive class. So I will be talking to you, and you'll be talking back to me. But when you're not talking, when I'm talking, I hope you'll turn off your mics. So right now you can open your mics and tell me what you understand about or what you know about three-phase systems.
Sir, there are two types. Um, or should I say types? There are two types of three-phase systems. Delta and star connections.
Okay. There are actually more, but those are the two main ones.
Well, yeah, two main.
All right, good. Good. All right. So where can we find three-phase systems?
The power station generates voltage using three phases, or outputs them in three phases. And for the most part, until it reaches the transformer that goes into your house, it usually comes down in three phases.
Okay, very good. Very good. It look like you read my first slide there, man. Right, Mr. Johnson.
No, sir.
Speaking from experience.
No, sir. Just common knowledge.
Okay. All right. Good. All right. So yes. All right. So let me bring back up my screen. All right. So yes, on the right of this slide here, you will see what is called a power system layout. So a power system, which consists of generating systems, transmission systems, distribution systems. Uh, in some countries, like the first world countries, where they have very high voltages, they have what they call transmission and subtransmission. But we don't have the transmission voltages except for 138 that they're talking about. So our transmission voltages are actually 138 and 69 kV. And then we distribute at lower voltages, 24 kV, 13.8 kV, 12 kV, 6.9 kV. I don't think we have any more 4 kVs. It could be for the bauxite companies. All right, so a little bit about myself. I used to work at JPS, and I used to do a couple jobs. We used to control the whole operation at the power system, right? And then after a while, I did some planning. I went in the planning department and did planning especially for the distribution system. So I know a little bit about power system. So I'm actually a power system engineer. And I know a little bit about what goes on with all of the different equipment in the power system. So, as Mr. Johnson rightly said, at the generating station, you have three-phase system, and this is kind of indicated by the three lines coming out. And also at the transmission level, you have three-phase system. At the primary distribution, there's also three-phase, so them in green over here, right? And then at the secondary now, we have single phase, right? So all of that is stated here. So electricity is generated, transmitted, and distributed on a power system mainly as a three-phase power supply, right? But you can have single phase primary distribution, right? And so this is just detailing what constitutes a power system, a generating system, a transmission system, and a distribution system. Somebody coming in? No. Yeah. All right. And as we said, the distribution now is where you will experience some, especially on the secondary of the distribution system. That's on the other side of the pole-mounted transformers. That's where you will have some single-phase systems. All right. All right. So a little bit more about this. So I'm showing you now a diagram which constitutes a generator supplying three lines and a neutral. The neutral is the black here. So three lines, three-phase power. And the three-phase power is feeding a three-phase motor. And we have single phase going to a light bulb and also to some outlets, some plug outlets. All right. Now, as Mr. Bruce said that we can have two types of system, and we will talk about that shortly. But in the star system, you will see on the primary side, you will see 3 or 4 wires. We call them conductors or lines. So that's why they're labeled line 1, line 2, line 3. So you will see 3 or 4 on a star system and 3 for a delta system. So the 4th wire is the neutral conductor. All right. Any question on that so far? No?
No, sir.
No, sir.
No, sir.
All right. Oh, wow. All right. I must confess that I have this connection here is a free Zoom, the basic Zoom. So you're going to be kicked out in about 10 minutes. But what you could do is just log back in, just connect back, and come in. That's why I'd wanted to use the Google Meet, but I wasn't so sure how many of you actually can connect, because last semester more than half of the class couldn't connect to the UTech Google Classroom. So I did. It doesn't allow to record if it's not associated with a classroom. So I'd actually sent that link earlier, and then I realized that I couldn't record. All right. So
sir.
huh?
Yeah, one of us could record it.
Oh, okay. I don't know about that. All right, but I guess that's a possibility. All right. So when it closes, we just come back in. All right. And I apologize for that. I hope though that everybody can connect to Blackboard Collaborate also, because I was going to use that then, but somebody told me that it was giving some problems. One of the lecturers said that it was giving some problems, and they kicked them out also. So they had to I had to go back to Google. All right. So tell me, are you able to connect to Blackboard? Huh?
I haven't been able to as yet, sir.
Okay. Do you take Blackboard? Right. What about Google Meet? The Google Classroom.
I can connect it to sir.
From last semester, because last semester I was having problems with it. Half of the students couldn't connect to it because of I don't know. I don't want to say, but one of the things was
Sir,
that
UTech has some restrictions with Google Classroom. With the Google Meeting, if you're on UTech's Wi-Fi, there's some restrictions.
Oh. All right. I guess we'll figure it out. Go to meeting. All right. Is that free? Huh? All right. Let me write that down because I will try. I will look for that later on. Go to meeting. All right. All right. So again, I apologize. When it kicks you out, just come back in. All right. So there are not only 3-phase system, but there are single phase and 2-phase system. So the more common ones are the 3-phase and the single phase system, but you also have maybe a relic of the past, 2-phase systems. So this slide here is comparing single phase, 2-phase, and 3-phase. So the single phase system, as you can see, would be characterized by a single waveform, a sinusoidal waveform. A two-phase system would have two of them. And there is actually now a phase shift of 90 degrees between the two phases. The three-phase system has three sinusoidal waveforms, one for each phase. And then there is a 120-degree phase shift between the phases. And we'll talk about, we are looking, and this now we are looking at balanced systems. So when they are balanced, then the phase shift would be 120 degrees. And the magnitude, so note the peak values here, are all the same for a balanced system, whether it's two-phase or three-phase. Right? Magnitude is the same. For three-phase, the phase shift is 120 degrees. For two-phase, the phase shift is 90 degrees. Two-phase systems are rarely used, but induction motors, in a sense, kind of start as a two-phase system. Many of them are not true two-phase system because they don't have a 90 degree between them. But some of them are. So they kind of approximate a two-phase system. But once most of them are started, then one of the phases is taken out, or one of the winding is taken out, and they revert to a single phase operation. All right. But when we get to drives 2, we will look at that. All right. So the three-phase is our real focus, but just for comparison, I show you the difference between single phase, two-phase, and three-phase. All right. Now, the sinusoidal waveforms can actually be represented by equations, as you know. So these are sine waves. So for the single phase, it would be VA equal to sine theta. For the two-phase system, you have two equations, one for waveform A and one for waveform B. So VA, again, if we're considering these as voltage waveforms, VA would be sine theta, and then VB would be lagging behind by 90 degrees. So hence this minus 90 degrees. For the three-phase system, again, sine theta for the first one. And you could actually consider it as sine theta minus 0, because it's crossing it starts at a 0 here. It crosses the x-axis at a 0 point. Waveform B crosses it at 120, and waveform C crosses it at 240. So hence the minus 120 and the minus 240 for waveform B and C, right? Similar equations can be written for current. So if these are representing current, we could write similar current. So instead we would write IA, IB, and IC instead. All right. Now the waveforms can also be represented by phasors. All right. So these arrows here, what you probably are used to in maths as vectors, are the same, are electrical equivalent for phasors, right? So a phasor is what you would consider a vector, but vector is defined as having a magnitude and a direction, while a phasor would have a magnitude and an angle. All right. And the diagram is showing you how each point on the sine wave can be represented by a phasor. Right? And by the way, now the phasors rotate in an anti-clockwise direction. Right? Just like how you'd measure from maths in high school, you measure anti-clockwise. The same way we consider our phasors. Phasors rotates, right? So the phasors are rotating in an anti-clockwise direction. So as as long as the current or the voltage is on, this sine wave will be continually going. And say that again. All right, so we will pick up in a couple of minutes. All right.
And
Yeah, just rejoin. Rejoin. As soon as you see the link goes, you can rejoin. All right, so I'll stop share right now, and we'll pick up after.
Outside.
Are we all back now?
yes, sir.
Okay. All right. Somebody else is coming in. All right. Welcome back. Is everybody everybody back now?
Yes, sir.
Yes, sir.
Yes, sir.
All right. All right. Good. So yeah, we were discussing phasers, and pointing out the equivalence to what you learned already about vectors. All right. So in the phasers, the direction is given by an angle, right? And you can see where the different angles are located in this wheel, right? And we measure angles in the anticlockwise direction. So the phasers are rotated in the anticlockwise direction. When you get to do power systems, you will learn about positive sequence, negative sequence, and zero sequence. We are just operating in the positive sequence. So our phasers are for this module we are operating in the positive sequence. So our phasers are rotating in the anticlockwise direction, and we measure them in that direction, right? So we're going in this direction, going anticlockwise, the angles are positive. If we measure I should point out that your calculator, once the angle passes 180, and your calculator, the calculator starts to measure it this way. So you see a negative number instead, right? But this would be negative 150, but positive 210. So they are actually the same point. So just to point out though that your calculator once will measure some angles as a negative angle, but it is actually because it is operating in this area once the angle passes 180 degrees. All right. So you will see that. So nothing to worry about right now. So I have some examples of phasers, some examples of vectors. When we learn in high school, we talk about a vector will be 5 kilometers north or 10 kilometer east, northeast, etc. But the phasers now has a magnitude and an angle, right? So your house voltage, since it's single phase, you would only be having 110 at angle 0. But say we had a three-phase system, then these would be the angles for a three-phase supply. Right? So voltages can be written as phasors, currents can be written also. Right? And the phasors are rotating at a speed of measured in radians per second. Right? So that is something that you will get used to later on when we go on to DC machines, when we start to do some calculations with radians. All right, but omega, the angular velocity is equal to 2 pi f, where f is the frequency. All right, so that is something to just bear in mind for the time being. All right, now, as I said before, the waveforms can be represented as a sinusoid, so a sine wave.
I got mine.
Could that person mute their mic? All right, so we have them represented here, the waveforms represented and the equation for them is a sine wave. But we could also represent them as vectors, as you saw before, right? So when we represent them as vectors now, this is what they look like in this diagram here. So this would be a phasor diagram, not fully labeled yet, but just to show you the orientation of the red phase, the yellow phase, and the blue phase. So if we're measuring from here, the red phase is our reference. So this would be at angle 0. We move 120 degrees, we meet the blue phasor, and we move another 120 degrees, we meet the yellow phasor. All right. So going in that direction, you can see that there's a 120 degrees shift between the phasors. All right. If I am using the red phase as my reference, and they are rotating anti-clockwise, and let's say you're standing right here, so your eye is right where the doubler is, where the omega is, sorry. Your eye is right there, and the red phase is passing you. The next phase that you will see coming up would be the yellow phase. So the yellow phase would be lagging the red phase, and it will lagging it by 120 degrees. And then as the rotation continues, the blue phase will be the last phase you see, and that would be lagging the red phase by 240 degrees. This 120 plus this 120, 240 degrees. All right. So that is what is written down here. Red phasor is at let's assume it's a voltage phasor. It's at angle 0. The yellow phasor would be lagging that red phasor, and that you can see that here in the waveform also, by 120 degrees. And then the blue phasor lags the red phasor by 240 degrees. So how we can distinguish the lag? You can look at the peak, or you can look at where they cross the horizontal axis, rising. And so the red phase is rising, and it crosses the x-axis or the horizontal axis at angle 0. The yellow is rising here, and it crosses the horizontal axis at 120. The blue is rising here, and it crosses the horizontal axis at 240. So that is how you can tell where they are, what the phase shift is between them. So you could either look at where they peak, as shown on this diagram, or you could look at where they cross the horizontal axis as they are rising. All right. So Vy lags Vr by 120, Vb lags Vr by 240. All right. But we could also write it this way. Since we're measuring this way now, measuring anti-clockwise, we could say that Vr is at angle 0, Vb would be at angle 120. So that's what we have down here. And Vy would be this 120 plus this 120 at angle 240. All right. So we locate Vy at angle 240 and Vb at angle 120. Vr at angle 0. Now the V here, the magnitude, is the RMS value of the voltage. Right? So when you see a voltage in a problem, it's the RMS value, the root mean square value of the voltage. Right? And we could have, this could be the phasor for currents also. So we could write similar equations for currents. All right, now Mr. Bruce had mentioned that there are two types of three-phase systems. All right, so we said two main types, but we'll be looking at them. So this is the configuration of the star connected system. All right. So notice how they are connected. This looks like an upside down Y, right? It's also called a Y system because of that, right? And on the right here, we have a delta connected system, right? And the delta, so you can see it basically have a triangular orientation. So the delta is also called a mesh system. So you may read something and say a mesh circuit. They're actually talking about the delta system, right? The three-phase mesh system, talking about the delta. All right, so we will focus today, though, mainly on the star system. And the diagrams here shows you two three-phase systems. A generator connected to a load via some. Yes.
Is it that the delta doesn't have a neutral connection?
Right. So there's no physical neutral in the delta. Right. But there's actually a neutral point, a fictitious neutral point, right here, right at this point here, where the arrow is pointing. But there's no physical neutral.
Okay.
All right. All right. So I'm showing you two three-phase star-connected system. So on the left here, we're seeing the generator coils connected in star, the generator windings connected in star. And down here we have, on the right, we have a load. And it's also connected in star. And so the generator is connected to the load by either transmission or distribution lines. All right. Don't pay too much attention to the current right now, but what it is basically saying is that if you look at this, 5 amps is going to the load on this phase, on the red phase, or the red line, and also on the blue line. But if you notice now, 10 amps, so the sum of those two 5 is coming back to the source, right? So you're going to always find that you have a cycle. The current completing a circle, a cycle, or a closed circuit. Yeah, that is the term I need to say. So you have a closed circuit. So current leaving from the generator, but it's also coming back to the generator from the load.
Sir.
All right. Yes.
Normally 4 wires are connected to the star configuration.
All right. So this is pointing out that you can have either three-phase, three-wire star system, right? And if you look on the right, you can have a three-phase, four-wire system, right? So we are used to the three-phase, four-wire system, but you can have a three-phase, three-wire systems also, star systems. So the neutral, notice now, so there's no connection between the neutral. So this neutral, right, like here on the right, you have the neutral between here and here. And this one now, there's no neutral. It would have to be connected this way. There's no neutral in this one. And later on this afternoon, we will this evening we will speak a little bit more about three-phase, three-wire systems and three-phase, four-wire systems. All right, but yes, it is possible to have three-phase, three-wire for the star also.
All right.
All right. All right, so let us look a little bit more closely now at a star connected load. So this is a star connected load, and it is being supplied by a generator that is not seen, right? Um, I normally would have a, a rectangular box here and write three-phase supply. I put in the voltage and the frequency. All right, but so just use your imagination now and picture that there is a three-phase source here, right? And since there's a neutral, it's most likely it's a star-connected source also. All right, so the currents that are flowing on the line from the source to the load are called line currents. Right? So line currents would be IR. So it's coming from the source. So notice the direction of the arrow coming from the source to the load. You have IY also coming from the source to the load, and IB coming from the source to the load. And then you have the neutral conductor, and you see the current arrow pointing away from the load, so which means that it is going back towards the source, right? So the line currents are IR, IY, and IB. Notice also that we have some voltage indication on the diagram. So between this red line and the neutral is what is called a phase voltage. All right, so the phase voltage now is between a line and the neutral. So we have one phase here, VR, one phase voltage, VR, another one here between the yellow line and the neutral, VY, and another one between the blue line and the neutral, and that's called VB, right? So the phase voltages are VR, VY, and VB. All right. The name can be adjusted, and we'll get to that in the next slide. But notice there's also some other voltages. We have VRY, we have VBR, and VYB. Now, these are voltages between two lines. So these are measured between any two lines. So between the red line and the yellow line here, we have VRY. Between the yellow line and the blue line, we have YB. And between the blue line and the red line, we have VBR. All right, so line voltages will have two subscripts for the lines, two line subscripts. The phase voltages can be written as this, or it can also be written as VRN, VYN, and VBN. So we'll get to that a little later. All right. Any questions so far?
No, sir.
No, sir.
Okay, good. All right. This looks like a breeze. All right. So on the diagram, notice also that we have some load impedances. Right. So in each phase, you have a load impedance. So in the red phase, in the blue phase, in the yellow phase, you have a load impedance. And these impedances are ZR, and that impedance is connected now between the red line terminal and the neutral, right? So this would be your red phase. This would be your yellow phase. So between this terminal for the yellow line and the neutral, that will be your yellow phase. And between the terminal for the blue line and the neutral, you have the blue phase, right? So these impedances are in the phase. All right, so this is just making the point that for the star connected load, the loads are connected in each phase between a line conductor and the neutral pointer conductor. For the three-wire system, you will not have any neutral conductor, so that's why I put point also. The three-phase three-wire system. And so we give names to the impedances in each phase: ZR, ZY, and ZB. All right. The diagram also shows the neutral, the current. All right. And that will be taken back current. So you will have things like this, a flow like this, along the red line, through the neutral back to the source, along the yellow line, through the neutral back to the source, and along the blue line, through the neutral back to the source. All right. So that's basically the paths that the currents travel. All right. Now the current flowing in the phase through the phase, I should have said through. All right, through the phase impedances are known as phase currents. All right, so the current flowing through this impedance here is a phase current. All right. Now, if you observe, you will realize that the line current flowing along the line here, is also the same current flowing through the phase. Right? So for all of them, the line current here is also, since there's no other path for the current to flow at this point, the current flowing in the line is also the current flowing through the phase, and similarly here. All right, so for a star connected system, the line current and the phase currents are the same. All right, so that is what is stated here in bold red. The line current equal to phase current. And IL representing line, the L representing line, and the P here representing phase. So IL is equal to I phase for a star connected load. Whether it's balanced or not, I line is equal to I phase. If it's unbalanced, then the values for IR, IY, and IB may be different in terms of magnitude and angle or angle. All right. So, but we'll get to that. So whatever is flowing in the red line, will be flowing in the red phase. Whatever is flowing in the yellow line will be flowing in the yellow phase. And whatever is flowing in the blue line would also be flowing in the blue phase. All right. Hence, IL is equal to I phase.
What exactly mean by balance?
We'll get to that. But yeah, good question. So that you're thinking. We'll get to that shortly. All right. So just give me a couple minutes. All right. All right. So the voltage across a phase impedance, as we said before, are VR, VY, and VB. All right. And as I pointed out earlier too, that just a short while ago, that they can also be written as VRN, VYN, and VBN. And this is because the phase voltage is measured between the terminals of each phase, right, R line, and the neutral. So there's a reference to the neutral in the naming of the voltage. All right, so the phase voltage across ZR is VR or VRN. Just going in a whole heap of details to tell you what I just tell you. Across ZY is VY or VYN, and across ZB it's VB or VBN. All right, by definition, the voltage between any two lines is called a line voltage. So we have a voltage between the red line and the yellow line. That's a line voltage, and that would be named VRY. The voltage between the yellow line and the blue line is called VYB, and the voltage between the blue line and the red line is called VBR. All right, there's a particular reason why these are the namings are like this, and I will tell you about that. It has to do with something called phase sequence, or the sequence in which the phases are moving. All right, but I will tell you about that at another time. All right. So the phase and line voltages can be written as phasors. All right, and the phase voltage as phasors would be like these. So VRN we say would be our reference, so it's at angle 0. V is the magnitude of the voltage. We don't put a real value here. We just put a V. But when we get to a real problem now, then we put a number there. And VYN, V angle 240, and VBN, V at angle 120. All right, and this is saying that the red phase voltage is our reference phasor for a star system. So note that the red phase voltage is the reference phasor. So the red phase voltage we will always use as at angle 0 for our star system. Don't be confused though if you see other books use heroes. Other books use other orientation for the phasors. So don't be confused. We are using this, right? And that is what the waveforms also indicate. All right. Now, what is the mathematical relationship between line voltages and phase voltages in a star system? All right. So I've put a voltmeter here to measure my line voltages, right? So this voltmeter now is measuring the voltage between the red line and the yellow line. All right. So it's connected to measure VRY. All right. Now, if you look at this, you will realize that the voltmeter is actually measuring the sum of two voltages. It is measuring the voltage across here from R to N, and it's also measuring the voltage from N to Y, right? So this is a vector or phasor addition. So if you think about traveling from red to yellow, you would travel from R down to N, R down to N, and then from N down to Y. All right. So VRY would be VRN plus VNY. All right. So that's what this is saying. All right. Now, to find that relationship, we have to go through the second exercise. So I bring this back just to help in your recollection that VRN is that, VYN is that, and VBN is that. Now, VNY, we didn't define VNY, but we define VYN as V angle 240. But VNY is actually minus VYN, if you remember your vectors. So just switching around the subscripts here means that you're actually reversing direction. So therefore, VRY is equal to VRN plus VYN. and then that can be written as VRN minus VYN. And then we had defined these already, VRN as V angle 0 and VYN as V angle 240. So if we do the maths, complex numbers on your calculator, you will end up with root 3 V at angle 30. So VRY would be root 3 V at angle 30. And we can do the same thing for VYB, calculate VYB, and it would be, so VYB would be from here down to here. So notice now we're moving from Y to N, right? And then from N down to B, right, to get here, right? So VYN plus VNB, but VNB is equal to minus VBN. So we can substitute our values here again. And we get V angle 240 minus V angle 120. And we end up with root 3 V at angle 270 degrees. Now, as I told you before, your calculator would say it's at angle 90 degrees or minus I. So I represent it here also, so that you will know that it's the same thing. All right. So what I would want you to do in the next 10 minutes or so, so this is your activity now, prove that VBR is equal to root 3 V at angle 150, right? And this is coming at an opportune time because we're running out of time again. This thing has been scratching my head. All right, so yeah, just spend some time now and say that again.
No, I was asking if you're able to hear me.
Yeah, go ahead.
I was just asking if you could use Google Meets instead. That way we wouldn't have the time problem.
All right, the Google Meet, if it's not connected to an institution, won't allow recording.
So, really?
Yeah.
Okay.
So that's why I had to cancel the first link. So if it's not associated with an institution, it's not going to allow you to record. So that is why I came back to this. If I can get the university to pay for this, then we'll use this. Otherwise, somebody suggested go to meeting. So I will look at that and see how that can work.
Sir,
all right.
Previous slide, please.
All right, the previous slide. All right, right. So you basically want to calculate VBR. So you can use this information. And I'll give you about 10 minutes. So when this kicks us out, you can come back in. Maybe around as soon as you can after that. But in the meantime, you can work on proving that VBR is equal to this. Root 3 V at angle 150. All right. So we will stop here. And then
hold on. Go back to the last slide for a second, please.
This one?
Yeah.
All right.
All right, thanks.
Okay. All right. Normally, when I have everybody's email address, I will send them the notes ahead of time too. That was the usual practice. So I need everybody's email. I don't know who I can ask to get it for me. The alternative would be everybody sending me their email individually.
I have a Google sheet with about 20 names on it so far with the emails. I just waiting on the rest of them to fill out the put in the name on the Google Sheet.
Okay. All right. Good. Good. Who is this? I didn't see.
Johnson.
Who?
Antonio Johnson.
Oh, Antonio. All right.
So you can go back to the previous slide.
What are the phases that you need to add?
Sir, VVN and VRN.
You add those?
No, sir. It's VBN minus VNR.
Go again.
It is VBR is VBN minus VNR.
All right. Look at how we did it here. Look at the.
No, sir. So with the VBN plus VNR or VBN minus VRN.
Right. All right. So
So,
if you try that, yeah.
so one thing, when I did it first, I didn't get the right thing because I had my calculator in radians. So you have to check that the calculator is in degrees.
Right.
Yeah.
Yes. Right. Yeah, that's an important point. All right. So everybody know what to do now, though. Basically, you follow these steps. So that's what I asked you to do before. Just break it down like this, like how we did for VRY and for BYB. So it's very similar. You remember how we define these. All right. So if from our analysis now we find that VBR is equal to root 3 V at angle 150, VYB root 3 V at angle 270, and VRY root 3 V at angle 30. If you look, if you were to draw these phases, and we soon show you them drawn, you would notice something. But let us look at the magnitude first, right? So if we consider the magnitude of the phase voltage phasors and the line voltage phasor. Somebody saying something?
Yes, sir. I have a question.
Yeah.
On the previous slide, if you when you have the 27, when you get a negative, it doesn't matter, right? As in, why you change the 270 to the minus 90?
I put this there. This is the positive is really what we measure, right? But your calculator will give you minus 90 or minus I. So that's why I put it there so that you will know that you are not wrong. Minus I is the same as minus 90 degrees. When you work out the values, you get a minus I on your calculator. So I put that there to show you that you're not incorrect. But this, since we're measure anti-clockwise and positive values.
She's currently on the phone. She's currently on the phone.
Say it again?
Boy, grass.
Could you turn off your mic? All right, so VP is the phase voltage. And VL is the line voltage.
Make space, dad.
What's
But
going
the
on
big
here?
man call me. Where the man has several mission.
Sir, can't you mute the mic, sir?
Let me see who. I'm not sure.
You removed him, right, sir? Cool, cool.
Remove him?
I was asking if you did remove him.
No, sir, I'm not turn off him mic now.
Yes,
I'm
sir,
not turn
mic
off
off,
him.
sir.
All right. All right. So the phase voltage has a magnitude of V, and the line voltage VR. So yeah, just to go back, the phase voltages have a magnitude of V, right? And the line voltages have a magnitude of root 3 V, right? So that's what we see here. Line voltage, a magnitude of root 3 V. All right, so if we consider only the magnitudes now, the VP is the magnitude of the phase voltage, and VL is the magnitude of the line voltage. So if VP is the magnitude of the phase voltage, then VP would be equal to V as before. VP would be equal to V, and VL would be equal to root 3 V, right? But since V is equal to VP, then we can say that VL is equal to root 3 VP. So V line is equal to root 3 times V phase. All right? So that's a relationship for a star connected system also. The line voltage is equal to root 3 times the magnitude of the phase voltage. So without considering the angles, just looking at the magnitudes, we have this relationship. VL is equal to root 3 V phase. And remember that we had IL is equal to I phase also for the star system. So those are two relationships that you need to remember. And somebody asked about a balanced system now. So these are the characteristics of a balanced system. The phase voltages or currents are equal in magnitude. All right, so we saw where all of the phase voltages had value V, right? The phase voltages also have a phase shift of 120 degrees between them, between any two of them, right? If we look at the line voltages or currents also, they will also be equal in magnitude. So we saw where all of them had a magnitude of root 3 V, right? And in a little while, you will see that all of them also have a 120 degree phase shift between any two phases. So a characteristic of a balanced system is that the voltage magnitude, the phase voltage magnitudes are the same. The phase currents are the same magnitude. The line voltages have their own same magnitudes. And between any two phases, whether phase or line, between any two phase voltage phases, you have 120 degrees. And between any two line voltage phases, you have 120 degrees. Now, what will actually make the system balance also is that the impedances in each phase are equal. So therefore, we had ZR equal ZY equal ZB, and it equal to some value at some angle, right? All right, so this is now the phases for the phase voltage. So VRN is here, VYN is down here, and VBN is up here at 120. And VRY is at 30 degrees here. VYB is at 270, or if you measure it this way, minus 90. But remember, we measure anti-clockwise, so that's why we have the 270. And VBR is this. All right, measuring this way, at 150 degrees. So if you look at it between 30 and 150, that's 120 degrees. Between 150 and 270, that's another 120 degrees. So between the line voltage phasors, you have 120 degrees. And between the 270 and the 30, you also have another 120 degrees. So the line voltage phasors are also showing that they are 120 degrees apart. All right? All right, what am I saying here? All right, so this is the phase voltage phasor for a star connected system. All right, yes, important now, important to note that in this module, our voltage phasors are going to always be balanced. So the phase voltages are always going to be balanced. They're going to have the same magnitude and they're going to have 120 degrees between each of them. And the line voltages are also going to be balanced, have same magnitude and 120 degrees between them. So this is what we're, this is how we're going to restrict ourselves in this module. When you're doing power systems, you won't have everything always balanced. Voltage can be unbalanced. All right, but that is outside of the scope of this class. All right, so make a note, voltages will always be balanced. Both phase voltage and line voltage for this module, for this course.
Sir.
Yes.
So, sir, for clarification, so the line voltages would be equal. Is it that the line voltages would be equal to themselves, or they would also be equal to the phase voltages?
You tell me.
To themselves.
Right, they are equal to themselves, right? So, right, line voltages are equal to line voltages in terms of magnitude. And for the star system, in the delta system, you will see something a little bit different. So line voltages have the same magnitude. Phase voltages have the same, a different magnitude for the star system, but all of the phase voltages have the same. So I hope you're with me. So if the phase voltages are 100 volts, VR, VY, and VB would all be 100 volts in terms of magnitude. And they would be at 0, 240, and 120 degrees, respectively. Whereas now the line voltage, if the phase voltage is 100, then the line voltage would be 173.21 volts, right? And the red phase would be at, the RY phase would be at 30 degrees. The yellow phase would be 173.21 at angle 270. And the blue-red line would be 173.21 at angle 150. Hope I didn't confuse anybody a while ago. But so the line voltages will have the same magnitude among themselves, and the phase voltage will have their own magnitude among themselves. All right. So hopefully that is clear.
Oh, clear.
All right. Good. All right. Now, just a reminder, some things that you would have done from your first year that there's you should have done. There's a relationship between voltage and current phasors for different type of loads, right? So you can have a purely resistive load, a purely inductive load, an inductor, and a purely capacitive load, a pure capacitor, right? All right, so if you connect a voltage across those loads, AC voltage, you will have the voltage waveform showing here in blue, and the current also showing in red. Now for a purely resistive load, the voltage and the current phasors are in phase, and that is drawn like this down here. All right, sinusoidally you can see that they cross the horizontal axis at the same points, and they peak at the same point, so they are in phase. And then you draw the phasors in phase like this, right? All right. So V is the reference phasor, so I would be in phase with it. So they are both at the same angle. In this case, angle 0. Because a purely resistive load would be at angle, would have a resistance angle of 0. For a purely inductive load, the current lags the voltage. So we always, when we talk about lagging and leading, we're looking at what the current does. So the current is lagging the voltage by 90 degrees for a purely inductive load. And for a purely capacitive load, the current is actually leading the voltage, right, by 90 degrees. All right, so that's what these phasors are showing. All right. Now, loads are not only just purely resistive or purely inductive or purely capacitive. You can have combinations of these. So, for example, you can have RL. For example, an inductor would actually have some resistance in it. And you can have RC circuits also. Or you can have all of them combined, right? Now, the phase shift between these, so we see no phase shift here. We see a phase shift here. We see a phase shift here. The phase shift now will be dependent on the values of the R and the L and the C and etc. All right, so that's what this is saying down here. All right, and that leads us to the impedance triangle. So we have our impedance triangle for our RL circuit here. All right, so this is the triangle. But you can also develop voltage relationship across the resistance and across the inductance. Right? All right, the inductor. So this is called a reactance. The X stands for reactance. All right, so XL would be an inductive reactance. So this is the impedance triangle. So the XL points vertically upwards, and Z is the vector sum or the phasor sum of R and XL. And down here we have the impedance triangle for a RC circuit. Again, XC now representing the capacitive reactance is pointing vertically down on the imaginary axis. So we have a negative orientation for XC. All right, the power factor is cos theta. So you know how to work out cos theta. Adjacent over hypotenuse. Right? So, oh, by the way, yeah, the impedance triangle is a right angle triangle. So you can use Pythagoras to solve it also, which is what this is showing. Right? And so the power factor can be calculated from R over Z, power factor of the particular load. And the same thing over here for the RC load. Right? So this is something I know that you know already. So it's just basically a review. All right, so let's see. We have an example here. And right, so the question says that there is a three-phase load, each of resistance 30 ohm, are connected in star to our 415 volt three-phase supply. We should determine the system phase voltages, the phase currents, the line currents, and the neutral currents. So this is a very simple question. You would have known how to do it already from what we have done so far, I hope. All right, but let's get into it. So I have the solution for you, but you will also do some for yourself. All right, so something to note. You see this value of voltage that you have in the problem? Always assume that it's a line voltage unless you are told otherwise. All right, so this is the voltage between any two lines. All right, so this is what this is saying. Unless otherwise stated, the voltage value given in a problem is a line voltage. All right, so from the problem we had, since it's a star system, VL is equal to root 3 V phase, and we know that VL was equal to 415 volts. So calculating the magnitude of the phase voltage, it will be VL over root 3, and so that's 415 over root 3, and that's 239.6 volts. So we can now write our phasors. VRN is 239.6 at angle 0. VYN is 239.6 at angle 240. And VBN is 239.6 at 120. All right, so once we define our voltages, then we can find our currents. So we were told that the impedance, all of the impedances were 30 ohm resistors, right? So a resistor now would be at angle 0. So IR is equal to VR. So this current here that is flowing through here would be equal to the voltage across here, which is VR or VRN, divided by the impedance. So make sure you understand this now. To find the current in a phase, it's going to be the phase voltage divided by the phase impedance. All right? And you're going to always start out by trying to find the phase currents. Right? Whether it's star or delta system, start out by trying to find the phase currents. So phase current is equal to a phase voltage divided by a phase impedance. All right, and then we write our values like this. By the way, you can't forget your angles, you know, because you know you forget your angles, you lose half of your marks already. All right, even writing these down without the angles, you lose half of your marks. All right? So, right, you must put them in your calculator. Right. So phase currents, phase voltage over phase impedance. So IR is the 239.6, sorry, at angle 0, and ZR is 30 at angle 0, so that works out to be 7.99. VY is 239.6 at angle 240, and that divided by 30 again, and that's 7.99 at angle 240. And IB, VBN over ZB, and that 239.6 angle 120 over 30. So again, that is 7.99 angle 120. All right, so we can see that all of the phase currents have the same magnitude. Hence, we know that it's and the angles are 120 degrees apart. And so that verifies that it's a balanced system. But we knew before because we know that all the loads were the same value and the voltages were balanced already. All right. Now for a star system, the line current is equal to the phase current. So therefore, the line currents are equal to the phase current up here. So I just basically write them back. All right. All right. You won't get
that's a quick question. There's a quick question. So
yes,
the line voltage, right? It's basically a vector sum of VRN plus VNY, right? That would be the line voltage.
Right, for VR, right.
Okay.
For VRY, yes. For VRY. And it's the same for the others. So I will send you the notes as soon as I get your contact information, and you can read it over.
Okay.
And I will also send send textbooks. They are posted in the Moodle thing already, so hopefully that will be sorted out soon. All right, so the final question was to calculate the current in the neutral conductor. All right, now this is where you get back to your networks, and we look at current going into this node. So current going into this node is IR and IB and IY, and current leaving this node is IN. So we use Kirchhoff current law now to work out what the current is in the neutral conductor, right? So when you're telling what you're doing, you say using KCL, IN is equal to IR plus IY plus IB, right? And so therefore we just add up all the currents magnitude and angles, and then we get In is equal to 0. So for a balanced system, balanced three-phase system, the neutral current is going to be equal to 0, right? And this is why theoretically you can do without the neutral conductor, right? Because if no current is in there, it's basically not doing anything, right? But that is not advisable. All right. Yeah. So that is why we have you can have three-phase, three-wire system, but that is not advisable because your system, a fault can develop on any one of your phases, and if there's not a means of protecting the circuit, the system can burn, right, with a fault current. So the neutral is usually used in the protection of the system, right? So if you're doing power system protection, you will realize the importance of the neutral conductor in protection. And so it is not advisable, although it might cost you a little bit more to run an extra wire to have this three-phase, three-wire system. Only way you can do that is if you can guarantee that there will be no faults, and nobody can really do that. All right, so three-phase, four-wire is a better thing. All right, so this is your exercise. This is the last thing that we will do. I will send you the thing, but this is your activity, and this is where. So what you can do is see if you can get this done now. Right, I've given you the answers also, so you will know what your solutions are. All right, so we have about 6 minutes, so you can start working on it. It's basically the same kind of procedure as we did before, but now this time we have an unbalanced system. All right, any questions?
Where would this video be posted, sir?
As soon as I get your email address, I will send it to you, and it will be posted in Moodle when I get access to that.
Sure. Where can we get additional practice questions?
All right. I said that I will send you some books. I usually give students 3 e-books. But if you have been taught by me before, you probably would have had the Bird, the John Bird. So some practice questions are there. A lot of practice questions are there, but those are fairly simple because they only deal with balanced systems. And big people like you want to do it both unbalanced and balanced systems. So I will also send you the Hughes or post it. You will get the access to the Hughes, the Bird, and the Wildy. So these will give you all the questions that you need to practice.
All right,
Plus,
sure.
you'll get practice in class, like this one.
Sir, I have a question.
Yeah.
I see that there is a tutorial session.
Right.
I just want to know, sir, what's the plan for the tutorial session?
Practice, basically.
Oh, so we're just going to practice questions.
Right. Basically, that's right. Unless we become very desperate and we need to teach something, but I mean, it's just basically reinforcing what we'll be doing in the lecture sessions.
Oh, okay, sir.
All right. In previous years, sometimes I've used the tutorial sessions too for maybe little quizzes and things like that too. So be open to that also. All right. All right. Take care, everybody. So there are two tutorial sessions. Getting tongue tied. One at 5 o'clock tomorrow, and the other one at 6. So I will, I guess, between both of them, I will see you. Wow. Welcome, Miss Watson. All right. We're about to sign off now. So everyone, have a good evening.